Hello, welcome back. We are looking at proving memory and causality given a system's input-output relationship. So I have 5 different systems here, 5 different examples of input-output relationships. And we're going to, for each example, determine if the system is memoryless and if it is causal. And I've left the definitions up from the previous videos. You can read those there. Okay, so let's look at example 1. Example 1 says that the output at any certain time is the sine of the input at that same time. So, memoryless, for example, if I want the output at time 1, okay, that would be the sine of the input at time 1. Okay, or if I want the output at time 0, that would be the sine of the input at time 0. So you can see where we're going with this. The output at a certain time depends only on the input at that time. Yes, then we warp it with the sinusoid, but all we need is the input at that time. Y of t only depends on the input at that same time. So that is indeed memoryless. And I just want to call your attention to this again. We said something like this in the last video. This has to be true for every value of time. So notice I have a 1 here, and all I need is the x of 1. And I have y of 0, and all I need is x of 0. So for any y of t, all I need is x of t. For every value of time, that's going to be true. So yes, it is memoryless, and that implies causality. This is a causal system. And it's causal because it only depends on the previous and present values of the input, namely just present. Okay, let's look at example 2. Now there's a careful distinction to be made here. So this is y of t is x of sine of t. Now notice when I plug in 0 for t, y of 0 is x of sine of 0. Okay, well, what's sine of 0? Sine of 0 is 0. So we see that y, the output at time 0, depends only on the input at that time, time 0. So we might think, well, this is memoryless then. But remember, it has to be true for every value of time. And if I can just find one value of time, then that is disproving the property. Okay, all you need is one counterexample to disprove the property. So how about y of pi? So we can plug in integers, we can plug in non-integers for time because it's continuous. So y of pi, 3.14, right, is x of the sine of pi. And the sine of pi is also 0. So now we have something where the input at this time, 3.14, depends on the output at a previous time, 0. So that's not memoryless. Not memoryless. So we wonder then, is it causal? Because it seems as though the output is depending on the present value of the input and previous values of the input. Okay, well, I'll give you this counterexample. Let's say y of, how about negative pi over 2. So we plug in negative pi over 2. Negative pi over 2 is about negative 1.59, something like that. And so this would be the x of sine of negative pi over 2. Okay, so this is saying y of negative 1.59, something like that, is equal to x of, so what's the sine of negative pi over 2? And the sine of negative pi over 2 is negative 1. So this, now we compare, right? We want the output at negative 1.59, but we compare negative 1.59 to negative 1. Negative 1 happens later in time. So this now requires, or to get the output at negative 1.59 requires the input at a future time. So by definition, that is not causal. So that's our counterexample. All right, I'm going to erase that and move on. Feel free to pause the video. Okay, example 3. Y of n equals x of minus n. So this is a system that reverses the signal, time reversal. Okay, so we might plug in, now we can only plug in integers. So we might plug in 0 because it's discrete. And we would need x of 0. And we say, oh yeah, that could be memoryless then. I want the output right now at time n equals 0. All I need is the input at time n equals 0. However, if I plug in n equals 1, I need x of minus 1, something that happened in the past. So this is not memoryless. Okay, not memoryless. But it appears as though it's causal, right? If I plug in y of 2, I need something that happened in the past. So these values all happen in the past, relatively speaking. To get the output at 2, I need the input at minus 2. To get the output at 1, I need the input at minus 1. So we're tempted to say it's causal, except, remember, if I can just find one counterexample. What if I plug in a negative value for n, y of minus 1? So then I need something that happens in the future, x of 1. So this is not causal. Okay, now let's look at example 4. Y of t is equal to x of t times cosine of t plus 1. So is that memoryless? Well, you might be tempted to see this t plus 1 and say, oh no, that I need some different value of time, right? If I plug in t equals 0, then this is going to be cosine of 0 plus 1, or the cosine of 1, and that depends on future time. But remember, the definition is a system is memoryless if the output depends on the input at that same time. But so here's the input, right? So if I want, let's say, y of 0, change my color. If I want y of 0, yes, I have the cosine of 1, but look I have the input at that same time, 0. So what value of the input do I need, right? Here's the operative word here, input. I need it at the same time as the output. And since y of t, and so y of t and x of t, there are no shifts or any sort of squaring or scaling of time going on there, then this is always going to be true, that y of 1 is going to depend on x of 1. Y of pi will depend on x of pi. This cosine thing is just a scaling constant. So we conclude that, yes, this is memoryless. And then it follows that it's causal as well. Okay. Okay, you have to look at the input. 5. So in this system, y of n is a sum of the current, x of n, and all of the previous values. So this is an accumulator. Okay, the current output is a sum of all of the past inputs and the current input. K goes from -infinity to n. Okay, so is that memoryless? Certainly not. Not memoryless. Because of actually what I just said in English, it depends on previous values. So is it causal though? And it is causal. Because causality is a little looser in definition, and it allows present times and past times, input values at the present and the past. So an accumulator adds all of the inputs from present and from the past. And let's just be concrete here. If you didn't follow that, let's say we wanted the value of the output at time n equals 0. Well, if we expand the sum, this would be everything from -infinity, maybe to x of -2 plus x of -1 plus, and then all the way up to our n. So we're letting n equal 0. So this is a sum from k equals -infinity to 0. And then we stop the summation. So take a look here. So we want the output right now at time n equals 0. That requires the input at the present time n equals 0 and all of the previous inputs. So that's causal. And so you can think about different values of n and how that's going to change, but still we're only going to need the present and the previous values. So this is definitely a causal system.